this measurement and problem solving is an absolutely core concept. Like 90% of the problems that we're going to do in this class, you can solve with just manipulating units, with unit analysis. So one of the reasons that units are important, and this actually happened in December 11, 1998, NASA launched the Mars Climate Orbiter, which was going to be the first weather satellite around another planet in our solar system. Well, another planet other than Earth, period. But it came too close to Mars. So, they did all their calculations as best they could. They launched that thing out. They ran their maneuvers. Looked like it was going to be too close to Mars. So they had to do a course correction. Unfortunately, the company that made that course correction module, the computer, used, what did they use? They programmed it in metric units, so Newton seconds, measure of force. But the ground engineers at NASA were doing their calculations in English units, in pound seconds. And those are vastly different units. And so when they typed their numbers into the computer and sent the commands to the satellite, it did exactly what they said, but in Newton seconds instead of pound seconds. And it crashed into Mars and ended up destroying a $125 million, I think the satellite was just $125 million, not including all of the work and time and effort it took to launch it and get it to Mars and to monitor it. So units are critical. How likely is it that you're going to be in a situation where you could cause this kind of damage? Pretty unlikely. But especially if you go into nursing, it's very important to know the units of the, whatever medications you're giving to patients, right? If you give them a saline drip or something, or like a potassium drip or calcium, if they're, deficient in some mineral, potassium in too high a quantity will kill you. It stops your heart. So it's very important to be aware of what the units are, really in any situation. And so because of that, I will be grading lab reports and this unit analysis worksheet on whether or not you have your units on your answers. You can make sure you always have those units in there. It won't cost you the whole problem, but those little points will nickel and dime you to death. Okay, so in science, in general, we push the boundaries of very large and the very small, right? We saw that on Monday. I had that website where you could zoom all the way into the Planck length. You could see the size of an atom. You could also, I didn't do it on Monday, but you can zoom all the way out to the observable universe. So the scales that we're looking at in science can be either the smallest thing or the largest thing. And it's really not convenient to write out those super huge numbers or super small numbers with lots and lots of zeros. You also lose some information if you have too many zeros in large numbers. We'll get to sig figs though a little bit later. So to remedy this, we use something called scientific notation. And this is another very, very important thing. So if we want to write a number in scientific notation, we've got two different parts. There's the decimal part, so that's this yellow one here. And then there's the exponential part. And that's going to be 10 raised to some exponent n. Sorry, I was just realizing something about the way I have this set up, but it'll be fine if I want to write on the board. Anyways, so the decimal part is telling us sort of the significant number of digits that we have to work with. The times 10 to some power is telling us how many zeros are behind that. So it's sort of truncating this 9 zeros here for 14 billion. And if we wanted to write 14 billion in scientific notation, the decimal, right, is here. And we're going to move that decimal place over. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you usually want it to be a number between 1 and 10. So we're going to move it over one more, so it moves over 10 places. So if I take this, and now it's 1.4 times 10, and then how many decimal places we moved it over. So times 10 raised to the 10.
So basically with this, you would take the first number, and then how many numbers are after that would be your exponent?
Yep, for a really big number. And this works because if we take 10 and we raise it to the power of 10, that will give us, what is that going to be? This is what calculators are for. Although I think I know what my calculator is going to do if I do this. So 10, I did, yeah. So it's going to be a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros after it. So if we take 1.4 and now multiply it by that 10 billion, we'll get back to the really big number that we had before, right? So it's representing the same number in a different way.
So you put 10 up there, but you said it doesn't count the zeros. Isn't there 9 zeros?
There's 9 zeros, but there's also because we want our decimal portion, so we also move it over one more decimal place past the 4 too.
No, I'm talking about the 10 in the corner, in the top corner.
This one?
Yeah. Isn't that just how many zeros?
It's how many decimal places we moved. Yeah. And so because this is, and we'll do some more examples too, but because we want a number between 1 and 10 for our decimal portion, we moved it over past the 9 zeros, but then one more to go past that 4 to get that 1.4.
So that's why you put 10 there and 10 on the top? So the
Yes.
would always be the same?
No, this number will always be 10, this lower one. Because we're multiplying 10 by itself 10 times to get this big number, and then this times 1.4 will give us this number back. So this is this number, but it's a shorter way to write it.
So it's always 10 multiplied.
Yeah, always multiplied by 10 raised to some power. So let's look at, we'll move on here a little bit. So a positive exponent means we're multiplying, well, in this case it's 1 times 10, 1 times 10, 1 times 10 to the first, second, or third power. So that's 1 is 1. This would be just times 10 once. 10 raised to the first power, right? Exponents. Exponents mean you're multiplying that number by itself, however many times the exponent is. And then 1 times 10 raised to the second would mean that you're multiplying 1, that's this number here, by 10 twice. So multiply by 10 by 10. And then for 3, you're doing it 3 times. If this exponent is a negative number, again, this is 1 times 10, then we're actually dividing by 10. So 1 times 10 raised to the negative 1 means 1 divided by 10. 1 times 10 to the negative 2 means 1 divided by 10, and then divide by 10 again. And so on and so forth, right? And so if you have a number like this, 1 times 10 to the negative 3, it's representing a small number. Questions?
So, kinda, if you look at it, like, you have the negative exponent. If I'm looking at a pattern, that's how many zeros you have.
Mm-hmm.
So you could kinda, I mean, don't base it all on that, but that's how you can kinda check that's right.
Yeah, the other way to think about it, again, is in terms of how many decimal places you're moving it over. So if we zoom in on this one here. So if I have 1 times 10 to the negative 3, then I'm going to write 1. And currently, if I just have 1, the decimal place is there. So if it's a big number, we're moving that decimal place over to convert from our scientific back to standard notation. If we have a negative here, we're going to move it over 1, 2, 3. So if our decimal place is here, then there's 2 zeros in between there. And then if this is 1 times 10 to the positive 3, right, if we want to convert that to standard notation, now we have 1, and we put the decimal place here. And now where we want, because 1 times 10 to the 3, right, if you multiply something by 10, it's going to get bigger. So we're going to have a bigger number, so we move this back to the right, so it's 1, 2, 3. And so there's going to be 3 zeros in there.
So the first one though, you're supposed to have 3 zeros, no, the -3?
You're moving it over 3 decimal places because this 1 is taking up one of those places.
Okay.
Yeah. So it's not directly the number of zeros, but the number of decimal places that you're shifting. So you might ask the question though, like when do I use scientific notation? And really it's, if you have a number that's bigger than 10, or well, yeah, if you have a number that's bigger than 10 or smaller than, so if you have a number, greater than 10 or a number less than 0.01, then you want to start using scientific notation to represent that number because it's going to be shorter than the whole number, than the standard notation. So just remember, if a number is large, the exponent is going to be positive. If the number is small, the exponent is going to be negative. So for this 5,983, right, the decimal place is here, and we move that over 1, 2, 3 places, because that'll give us a number that's between 1 and 10. And so then when we rewrite this out, we write 5, and then we moved our decimal place here, 0.983. And then the times 10 to the third is what's holding on to the fact that this is not just 5.983, but it's 5,983. And then for small numbers, we're moving that decimal place. So doing the opposite of what we did on the previous slide. We're converting a standard notation into scientific notation. We take our decimal place, and again, we want to move it over so that our decimal notation is going to have a number between 1 and 10. So this is going to be 3.4, and then times 10 to the -4 because we moved that decimal place over 4 spots. And again, you'll get lots of practice this afternoon when we do this in the unit analysis worksheet. There'll be a lot of numbers that you need to convert to scientific notation. And actually, I don't remember if, I will double check. I have a scientific notation practice.
I think that's our homework too for chapter 2.
There will be, like in the homework for chapter 2, there's definitely practicing scientific notation. And then I have another whole worksheet that's just like, has numbers, and then it also has like answers on it, on the back. So you can try it and then check your answers real fast. So I don't think it's posted on Canvas right now, but I will post that. All right. I don't know what the national debt is now, but the national debt in 2016 was $18,416 billion. So that would be a very cumbersome number to write out every single time. So scientific notation definitely helps with this. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so our decimal place is here. So where am I going to move the decimal to without counting it right now? Where am I going to move the decimal to get a number between 1 and 10? To left? Between which two numbers?
1 and 8.
Yeah, so we're going to move the decimal place to here. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, you can use the commas if they're in there to help count, right? Because that would be 9 to there. 10, 11, 12, and then 13. So our number here is going to be 1.8416, and then we can add on the rest of those numbers as decimal places. This is going to be times 10, and then, right, 18 trillion is a big number. So our exponent here is going to be positive. Whoops, that's 3. It needs to be 13.
If that number wasn't so like even, but if you had like for the rest of the zeros, it was like 5, 4, 2, 7, 8. Would you still have to write that whole thing down before the x10?
We will get to that.
Yeah.
So yeah, that is sort of getting into significant figures, like how many decimal places do you keep, right? Like how many of those numbers actually matter. But we'll get there. And I guess this would be dollars. Cool. Any questions?
So is that what you were looking at in the answer, that we have it just like that? Or do you still want more to,
Yeah, this.
so that's all we have to do, just show how much where we moved it and then get that equation?
Mm-hmm. Yeah, that is scientific notation. Yeah.
Can we round the number, or does it have to stay like 4 numbers in the back of the decimal?
So that's significant figures again, but yeah, we'll get there. How to determine how many figures. You guys are thinking ahead. Problems that we haven't even covered yet. Were there any other questions on this? Yeah.
When you're asking us to show work on our assignment, do you want us to show you how we...
No, you don't need to show me converting it into scientific notation. I'll know if you did it right because the number that you have. Yeah, for showing work, it's like if any time you have to do any math, right? So for unit conversions especially, there's a lot of math. Homework 1, there's like one part of number 25 that has the smallest bit of math. Like you have to subtract 2 numbers. So you do want to see, even if it's just something as simple as 20 minus 5 equals 15, I don't know, put a unit on it because I want units, right? So if you have to do 20 minus 5, and that's the only math, I want to see that. But I just need to see some evidence that you actually thought through the problem on math problems rather than just writing down straight answers. I know that won't be the case for every single problem.
On the homework, you know how we use scratch paper? We could just put 1 and then do the answer. We don't have to write out the question.
No, you don't have to write out the question.
Okay.
Yeah, that's another good question. So yeah, just make it real clear, like that it's question 1. You can put your work, and when you write your answer, circle your answer. Always circle your answer. I know it's clear to you which number is the answer, but a lot of the times it's not to me. So I search for it. Do you have another question?
So when we're doing our chapter 2 homework, do you want us to, like, say this is the question, like, do you want us to solve the answer for that, or just show that? You know what I mean? Like,
Oh, I see what you mean. Yeah, because that is,
Because you could just put that in the calculator and it'll give you that.
yeah, if the number's big enough, it will. Or if you know how to change the settings on your calculator. I would say for chapter 2 homework, write out the whole number, move the decimal, and then write the answer, just for chapter 2 homework. In the future, there's going to be other stuff that you're doing, but if that's the only thing that you're doing, yeah, I do want to see that. All right. Okay, so now we've got a small number, 0.1234438. All right, so where do we move the decimal place? Between the 3 and the 8, yep. And so we're moving that over 1, 2, 3, 4, 5 places. So this is going to be 3.8 times 10. And then it's going to be a -5 or +5? -5. Yeah. You always need to, if you're converting something to scientific notation, there always needs to be this portion. because I've seen this. It's happened on other assignments and other classes where somebody will take this and they say, oh, I need to have scientific notation, and then they write 3.8. That's not the same number. It's a very, very, much bigger number than 0.000038. Okay, so now this is getting into, so that's scientific notation. Kind of gives you the basis to represent these large or small numbers. How many decimal places do we keep, though? That's significant figures. There are a lot of things that we can count easily in whole numbers, right? Like the number of people in this class. We go through and we can count, and it should be something like 24. Might be a little bit more, but you're not going to have a half person sitting in a chair. Right? The whole person, right? Count in whole people. So it's not hard to say that there are 24 people or 25 people exactly. Those are exact numbers. Other times, if you wanted to, for example, so like that's the 7 pennies here, our knowledge of the amount of a gold bar, the amount of gold in a gold bar, right, so 10 grams. Well, if you have you could probably do this experiment at home, right? You could take anything. I don't know how many gold bars you have sitting around at home. Hopefully you have a lot. That'd be nice. But you could take a gold bar and you could put it on your bathroom scale, right? Your bathroom scale only has a certain level of precision. But you know if you took that and you had a better scale, like a kitchen scale, you could get more digits out of the kitchen scale. And then if you had an even better scale, you could get even more digits. And if you had an even better scale, that could theoretically go on forever. But that's really hard to do, and a lot of the times pointless, right? We don't need to know with that level of precision what it is. But we do need to represent the level of precision that we do have. And so that's where the significant figures comes into play, is if you measure this on your kitchen scale and it gives you 1 decimal place, so let's say it gives you 10.0 grams, then you can't take this number and write 10.0000 grams, because that would be, in a sense, dishonest, right? You'd be lying to the next person who read that number that you had that much gold exactly. And you also wouldn't want to say that it's just 10 grams, because now you're losing precision. Now somebody could look at that and say, well, is it 10.1? Is it 10.2? Is it 10.9? So representing, really what we're doing with scientific notation is representing the accuracy, well, the precision of our instruments that we're using. So one example of this is, global warming temperatures. So scientists have concluded that the average global temperature has risen by 0.7 degrees C since 1880 to whenever this slide was written. This is based on analysis of records from thousands of temperature measuring stations around the world with varying levels of precision. So again, just like our gold bar, it would be different if we added zeros and said it's 0.70 degrees C. That's more precise than to say 0.7, or to say 0.700 degrees C. If we had all of these thousands of records and we type them in to calculate an average, your calculator doesn't know or care really about the level of precision that you enter in, right? Because if we put in 1 times 3, that's going to give us 3. If you type in 1.0 times 3, your calculator is still just going to say 3. And so in the same way, if you have numbers that don't multiply or divide evenly, you're going to get lots and lots of decimal places. So the scientists who did this research realized that the only level of precision that they could report was in the tenths place. And so they take this and they round to 0.7. And because the method for reporting numbers is standardized, anybody else who looks at this number will know that they measured it accurately to the ones place here, or to the tenths place, and then the next place No, sorry, I'm saying that wrong. For this number, it's actually measured accurately to the ones place, and then this 0.7 has some level of uncertainty to it because it's the last digit. So that last digit reported is always going to have the uncertainty.
And that was actually your question about rounding,
Mm-hmm.
get to the second, right?
Yes. Yeah. So, and we'll get into like how to do that calculation when you do math with numbers too. So again, every digit is certain except for the last, which is estimated. So here in this number, and for the rest of these examples, not the rest of them, but for a lot of the examples we're going to work with, I'm just going to tell you that these are the certain digits, and this is the uncertain one, and that'll tell us how many significant figures we have. But here, this is telling us these first ones are certain. Well, actually, this is just because it's how it's written. All right, these are certain, and then because this digit is the last one, that's the one that has some uncertainty in it, or is estimated. So if we get a better scale to measure our gold bar, then we can report that answer with more certainty in more decimal places before we have to estimate the last one. I think examples help here. So just like measuring a gold bar, right, we could get an infinitely better scales to get infinitely more precision. The same thing happens with how long something is. I recently started, well, I think I told you guys on Monday, I've been 3D printing, and yeah, the level of precision gets really important there. If you're trying to make two things fit together, there's a lot of things to take into account. And so if you're measuring something, you want to use the most precise tool available. A ruler is not the most precise. But if we were to measure this quarter, right, on this ruler, we have lines conveniently drawn in here to show us exactly where the edges are. But if we look at this, it lands in here between 20 and 30. And so now we have to figure out what do the individual tick marks in between mean. So this one's going to be, because it's halfway between, is 25. This one is going to be 24. And so this is where that estimation comes in, is we can say that this is bigger than 24. We know for certain it's bigger than 24, but it's less than 25. And so we estimate where, like how much bigger than 24 is it? And so here the answer they've got is 24.6, but we could say, it could maybe be 24.7, or it could be 24.5. Maybe not 24.5, it looks a little farther back, but we can't estimate any farther than that. Like we couldn't say that this is 24.56 because we don't even know if it's actually 24.5. And that would be misrepresenting the precision of our instrument. So you always measure to the certainty, and then you estimate how far past it is that line, how far it is past that line. This gets even more important if you have, is there a yard? Oh, there is, okay. This gets more important if you have less precise instruments. So for example, I mean, this is fairly precise, but this is what I was going to say. And again, this is one of those things that'll be looking for on lab reports especially, is that you are recording your numbers with the correct level of precision. Any questions on this so far? We'll get a couple more examples of measurements. All right. So fortunately, in our labs, we have digital scales. Those are easy because you just write down as many digits as there are. If you don't have a digital scale, though, you need to estimate what that precision is going to be. So this balance has markings of every 1 gram. So to estimate, or the position that we're going to estimate is the tenths place, right? Because we have 1 gram markings, so we need to say how far in between those marking, or the reading is. So here, this is 1 gram. And so, I don't know, somebody give me an estimate, how much this thing weighs in grams. 1.2, 1.5 even? Yeah, because which side of that line do you measure to? Is it the far side or the close side? But again, the estimate comes into play here. Now, if you were actually doing this, you would figure out which side that you need to actually measure to. I don't know for this one. But yeah, if you're measuring to the top, I know it's said in another place on the slide, you could say 1.2. But yeah, if you're measuring to the bottom of this line, then maybe 1.5 grams would be a good estimate. Yeah. And you try to obviously make the best judgment that you can, but the best is all you can do. So here's another example, but if we have a scale that has markings every 0.1 gram, then we need to estimate to the hundredths place. All right, so it's 1 past our smallest marking. And we can zoom this in. All right, so that's, switch colors here. This would be our 1 gram. So then this is 1.1. So what do you think this measurement is? It is 1. 1 point. 1 point. Well, this is whoops. This is 0.5. So it's this way would be larger. So 1.27, 1.26. Yeah. Yeah, so we will call this 1.26. I think that's what the slide says too. Yeah. Right. Grams. So it'll depend on the instrument that you're using. Let me just look a little bit ahead here. Okay. You do want to at least draw out an example of something that'll be important for lab. We'll do this one first. So if you have a thermometer to measure the temperature of a backyard hot tub, which this thermometer could very easily be reading the temperature outside today, record the temperature reading to the correct number of digits. So let me zoom this in for you here. So this is, just to be clear, this is 110. Sorry. 110 Fahrenheit. So how hot is this hot tub?
3.5.
Yeah, 103.5. I have the benefit of being able to look really close. Maybe 103.4. But yeah, somewhere in that area would be a very good estimate. All right, so switch markers again. 103.5 degrees Fahrenheit, or maybe 103.4. I'm just going to use a blank section of this slide. So one of the things that we do in lab a lot is we measure out volumes of liquids, and for that we use a graduated cylinder. So I'm just going to put some markings on here. Call that, and we'll call this, let's start at 3 mils, 4 mil, 5 mil, and then these will have that's a little rough. But when you're reading the volume of a liquid in a graduated cylinder, the water, it's usually what you're measuring, it's something in water, likes to stick to the sides, and it forms what's called a meniscus. Actually, let me exaggerate this. And so you'll kind of see this shape at the top of the liquid. And so when you're measuring this, you measure from the bottom of that contact lens looking shape. And I know my drawing here is just so excellent and precise, but what would you say that this measurement is? 3 point, again, yeah, so this is 5. Sorry, that's 0.5. This would be 0.6. 3.5, 6, 3.5, 2. Again, yeah, super rough drawing. But again, even on the graduated cylinders, you need to make sure that you're measuring to the correct level of precision. And for most of the graduated cylinders, it's going to be like the hundredths place, like this, right? 2 decimal places. Yeah, I'll cover some of the graduated cylinders are weird, and they don't have markings for every 0.1 milliliter. They have markings for every 0.2 milliliters, which I find frustrating. And on those ones, you can only do to the 10th place because you have to estimate in between 0.2 and 0.4 or 0.4 and 0.6. Okay. Are there any questions about measuring things? Cool. So now, significant figures. This is one that maybe if you've talked to other people who have taken Chem 20, people generally don't like significant figures. They don't have to be too confusing as long as you can remember there's like 3 rules. I think here they're listed as 4 rules, but it really comes down to 3. So when we make a measurement, and let's just use one of these that we did before. So if we have our 103.5, that's a good one. So we have 103.5. These are the rules for determining the number of significant figures. So you made a measurement, you've written down the correct level of precision. Now you need to determine how many significant figures you have. So the rules are all non-zero digits are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all of those always significant. So in our number here, our 1, our 3, and our 5, those are definitely significant digits. If we look at this first example here, 1 and 5, significant. And then these 2 1s are also going to be significant. That doesn't mean those are all of the significant digits. We've only done one rule. But the second rule, if you're reading ahead, interior zeros. So if you have a 0 that is in between 2 numbers that are not 0, sandwiched, that's going to be significant. So looking up at our 103.5, this is an interior 0. So that is also significant. We can even look back to number 1 here. Maybe I should do this in a different color. All right, so that's going to be, I'm going to do this one in a different color too. That is going to be significant. And let me try and, all right, so the blue is rule 2. So if we look at, do it like this. So looking at these other 2 examples here, we can apply rule 1 and say that 4, 2, and 8 are significant. And then we can apply rule 2 and say that these are interior zeros. So they're also significant. For this next example, right, 5 and 1, those are significant, and then the 0, interior 0, also significant. Then rule number 3, I gotta remember which colors look good on the screen. Whoops. Does that look? Yeah. Actually, is anybody in here a little bit colorblind like I am? No? Okay, cool. So you can probably tell that those are different colors. Easily tell. Hopefully. If you can't, you might be colorblind. You can take a test. It's very easy. Trailing zeros, this is rule 3. Trailing zeros are significant if there is a written decimal point. And I think this is the first one that gets a little bit tricky. There has to be a written decimal point. And there have to be zeros after a non-zero number. So let's go through these again. For our example I pulled from the other page, we don't have any trailing zeros, don't have to worry about it there. But going back to these examples for rule 1, right, this is 0, that's a written decimal point. These are leading zeros. But we have the one trailing 0 here, which would be significant according to rule 3. The examples in rule 2 don't have any. And then to go back here, right, these are non-zero numbers. Those are significant. This is a trailing 0, and we have a written decimal point. So that's significant. Then here we have non-zero number. And again, checking, we have a written decimal point, so all 3 of these are significant. And there isn't one here, but if you had this, how many significant figures does that have? How many significant digits? Just the 5, just 1, right? There's no written decimal point, and those 2 zeros are actually ambiguous because we don't know if those were made in a measurement or if they're just placeholders to make the number 500 instead of 5 or 50. So this is where you would need to use scientific notation to say how many significant figures there are. So we could rewrite this number now. If we rewrite it in scientific notation, let's say let's say this actually has. I did this measurement, and it's actually 2 significant figures. So I would write this as 5.0 times 10, and then just to go over this again, if we move this decimal place over 1, 2 places to the 2. So now we can reapply our significant figures rules to the scientific notation and say that, okay, 5 is a non-zero number, and now we have a written decimal point. So this trailing 0 is also significant. Cool? Questions? All right. I believe there's one more rule. Oh, I forgot that is the next one. So rule 4 is trailing zeros before an implied decimal point. Highlight this word. Implied meaning that there's not a decimal point written there. It's implied that it's there. Those are ambiguous. And again, you avoid those by using scientific notation. So 50,000, how would I write 50,000? And let's say that these both have 2 sig figs, 2 sig figs. I know that because I'm the researcher who took those measurements, right? So these have 2 sig figs. How would I write 50,000 to show that I have 2 sig figs? 5.0. Yeah, times 10 to the 4. Now what about 10? 1.0 times 10 to the 1.
Remember yesterday, I was like, oh, I'm going to film this.
Yeah.
Now I feel different.
Good. Good. Yeah, we just hadn't talked about it yet.
Yeah, I was definitely studying that.
Yeah, and I think I'm going to move. I think I will be moving the deadline for the unit analysis worksheet back. We'll see how everybody feels after today and lab today specifically, because you got 3 dedicated hours to work on it. Okay, moving on though. Yeah, so when a number is expressed in scientific notation, all trailing zeros are significant, and that's because we're always going to have a written decimal point. So that's why I usually don't include Rule 4 or really Rule 5. Leading zeros are not significant, and this could even say never. So it doesn't matter if you have decimal places or if you have zeros in front of a non-zero number. Sorry, it would be in this direction for you guys. In front of a non-zero number, those are never significant. They're just placeholders. The only time you're going to see those are in really small numbers, right? Because I wouldn't write 10 as 0, 1, 0. This first 0 serves no purpose. Looks more like binary. So my suggestion to you is to always write out, and this is going to look weird again, but
another one. I have a question about in the trailing zeros, the 500 dot 0. How would you write that in
oh,
scientific notation?
great question. And this kind of comes back to how many decimal places do we keep when we write in scientific notation? So here, we would keep all of the significant ones. So I'm going to draw an arrow up here. So if we want to write this out, right, so we got 500.0. So where would we move the decimal place to?
5.0.
Yeah, it'll be 5, and then our decimal. And then how many zeros were significant? So there's 3 here, right? Because they're all trailing zeros and we have a written decimal. So this would be 5.000 times 10 to the 2. Yeah, that's a great question.
It would be 10 to the 2 because we only had to move the decimal 2, right?
Yeah, so even though we had this 0 here, we're really only concerned with how many places we move that decimal over. And so since we only moved that over 2 places, then that's what this is representing. Yeah. Cool. So I did mention this at the beginning, There are things, exact numbers, like counting the number of people in a room, the number of pennies, the number of, it's called discrete objects, right? You can see that this is one Apple Pencil. So counting of discrete objects, integral numbers that are part of an equation. So like, trying to think of a number that has a discrete, or an equation that has a discrete number in it. This is a physics one. I think I'm getting this right. 1/2 mv squared. I think that's kinetic energy. But this 1/2, which we could write as 0.5, right? Because that's an integral part of that equation, that has an infinite number, an unlimited number of significant figures. So that is an exact number. Another one that comes up are some of the unit conversions that we use are exact. So like 1 foot equals 12 inches. That's an exact conversion factor. 1 foot exactly would be exactly 12 inches. And then one of the weird ones, 1 inch, we'll get into metric units here. 1 inch is 2.54 centimeters exactly. So at some point, they redefined the inch. Well, I think the original inch was based on the width of the king's thumb, but now the inch is defined as 2.54 centimeters exactly. So when you're using these conversion factors, you don't need to worry about how many significant figures they have, because they're exact conversions, so they have unlimited significant figures. Yeah, so defined quantities. These would be defined quantities. All right, I do want to get to, well, we could do, I could do that in lecture 2. But so how many significant figures are in each of these numbers? All right, so start with A, of course. 4. Does anybody disagree with 4? Yeah, so this would be 4 sig figs, because they're all non-zero numbers. All right, what about B? 3? Are these trailing zeros or are these leading zeros? And leading zeros are never significant. So yeah, because we're only counting the trailing zeros here, this would be 3 sig figs. Just these 3. How about for C? Yeah, just 2. Again, because we have 2 non-zero numbers. Now, this is something that might come up later. You might think of this as like, wait, do we count the times 10 to the 3 or the times 10 to the 2? You don't. Those are really just telling you how many decimal places you've moved over. They're not part of the significant figures because they're just representing the real number, the whole number, in standard notation, and they're not part of your precision.
So the 10 to the 3 never gets counted as a significant figure.
Correct. Yeah, yeah. That exponential part of that does not get counted. All right, this next one's a little trickier. How many significant figures in either of those numbers?
1.
It's not 1.
0.
So we haven't talked about metric units yet, right? This is a centimeter. And this is saying a centimeter equals 0.01 meters. And this is a defined quantity. So that is the exact definition of what a centimeter is in relation to a meter. So it's unlimited. So just like 1 foot equals 12 inches, in this situation where we're using it as a defined quantity, so you can use one to define the other, those both have unlimited sig figs. I might have lost some people with that. You can say exact. Right. Yeah. The unlimited or exact. All right, for E, how many sig figs? Yep. 3. So 5. And then we have 2 trailing zeros, and we have a written decimal point. Yeah?
For the unlimited sig figs one, is it because there's different ways of like interpreting it, like across different like measurements that it's unlimited?
You can kind of think of it because it's not a measurement. So like the rest of these numbers, and this is where I think it helps to like actually start working with sig figs a little bit. Because you're going to have a number of sig figs, and it's going to depend on what you measure. But if you want to convert that unit, and we haven't gotten to unit conversions yet, but if you want to convert that unit into something else, you use the definition of that unit.
That's what I meant. Like no matter where you convert it, it's going to be
Oh.
the exact number, right?
Yes.
So that's why.
Yeah, no matter where you use this, it is exactly that. Yeah. Sorry, I misunderstood. All right, and for F, how many significant figures?
We didn't do E.
Oh, sorry, E.
Would it be the 3? Oh, it was the 3, huh?
Yeah, I didn't write the answer down, but yeah, it's 3. So what about F? This is a trick.
All 4?
It's a trick.
Trailing 0, there is a written decimal.
Is there a written decimal?
You have to put it in the scientific notation first.
Well, if we weren't the ones who took this measurement, we don't know how many sig figs there are. So this is ambiguous. You can't tell. Yeah. I don't know if I spelled that right. You get the point. It is right? Okay, good, thank you. Yeah, so you can only get an ambiguous number if it's a big number. And then you've got these trailing zeros, but no written decimal point. It's ambiguous. Okay, any other questions here? Yeah.
So if there was a decimal, what would it be?
Yeah, if it was a decimal. So if this was, let me do it, because I know it's kind of hard to see the bottom of the screen. This was 2100 decimal. Now how many is it? 4, because we have that written decimal. So trailing zeros, if there is a written decimal.
But for it to have a decimal, wouldn't you need to have a 0 after the?
Not necessarily. Well, if I put another 0 here, then that would increase the number of significant figures. And this is another reason that the better way to write this would be in scientific notation. So what would this look like in scientific notation? Yeah, 2.100, but times 10 to the 3, yeah.
So you always keep the zeros if the decimal is at the end?
Yes. So the decimal, yeah, because the decimal's there, we know those are significant, so we want to keep them.
Okay.
Yeah. You always keep the significant figures. Is that your question? Okay. Well, the next step here is what happens when we do some math with them. So if we start to do some calculations, let's say we multiply 2 numbers together, how many sig figs do you keep from that final answer? Because now you still want to represent your precision, but you did some calculations. So that's when you have to round, because your calculator doesn't know how many sig figs you have. It will just give you all of the decimal places. So you have to know how to round that. And then this one is super, super important, and I don't think I've highlighted it enough in the past. For calculations involving multiple steps, actually erase just back to here. And then I want to highlight this. Round only the final answer. Now, that means that if you are working on your calculator, it is highly beneficial to learn how your calculator works so that you don't have to retype numbers in. One of the reasons, this is one of many reasons that I recommend this calculator, you can actually store numbers from your calculations. And I could show you how to do that in the lab. So if you do one calculation, you can store that number for later. And then if you need to use it again, it'll keep all those decimal places. You don't have to write them down on your paper and then retype them into the calculator every time. So only round your final answer, because you can, in most of this class, you won't get significant errors, but in some calculations, those rounding errors stack up fast. So in multiple steps, you only round the final answer. We're getting close to the end of the time here, but we got enough to go over this. Okay, so in my mind, multiplication and division, those are the easiest ones for determining sig figs. You keep the same number of significant figures as the fewest significant figures. So if you're multiplying two numbers together, you count how many sig figs each of those has, and then in your final answer, you keep as many sig figs as the one of those numbers that has the fewest. So in this example, let's first go through and count the number of sig figs. So 5.02, how many sig figs is that? Oops, that's the eraser. So that's 3 sig figs. For 89.665, how many sig figs? 5 sig figs. 0.10? Yep, just 2 sig figs. Okay. So our fewest number of sig figs is 2. So our final answer should have how many sig figs? 2. So the final answer spit out by the calculator here, whole thing, right? Now, where do you start with the sig figs? The easy rule is you always start with the leftmost number. That's going to be your first significant figure. So here we start with the 4, so that's 1 sig fig, and 5, that would be our second sig fig. So the final answer here with the correct number of sig figs is going to be 45. So we round after that 5.
Should you write that as like 4.5 times 10 the first in order to clarify?
Yeah, because I did give you that rule of greater than 10. You can. And technically, you probably should. You definitely have to do it if you get like 40 or 50 or something that has, tens place and then a 0, then you have to. But yeah, so we could rewrite this in sig figs, or in scientific notation as 4.5 times 10 to the 1. All right, now for the second example, maybe we can just jump to how many sig figs should our final answer have? 3. Because this has 4 sig figs, all non-zero numbers, nice and easy, and then this has 3 sig figs. So then, yeah, our final answer here is going to have 3. So again, starting with the leftmost non-zero number. Yeah, so we're going to keep the 965, and then, yeah, now we got to bring in the rounding rules. So 0.96, and I think the next slide has this on there. But if the number after our last sig fig is 5 or greater, we round up. If it's 4 or less, we just drop everything and we leave it. So because we have a 9 here, this will be 0.966. Cool. Questions? All right, so multiplication and division, like I said, I think it's the easiest because you look at all the numbers in the math you did, whichever has the smallest number of sig figs. And rule of thumb, it's almost always going to be the number that you start with. Especially on the unit conversions, either the conversion's going to have more sig figs than your starting number, or you're going to be using exact conversions. So that starting number is almost always what determines your smallest number of sig figs for unit conversions, which are, again, most of what we do. Okay, so multiplication, division. This is the rounding. Again, you're looking at the number of sig figs that you have, and I think that underlining them is a great way to keep track. So here, we're assuming that these both are supposed to have 2 sig figs. So if this is significant and this is significant, look at the next number. Is it 5 or greater? If it's not, then we just drop and we leave. Our final answer is 2.3. On this one, again, 2 sig figs, but the number after the 3, our last sig fig, is 7, so we round that up to 2.4. So, yeah. If we get you can get situations too, so if we had 1.99, and this was supposed to have 2 sig figs, then we round that 9 up, and this 9 becomes now a 10, so this would be 2.0. Shoot. You know what, the nice thing about this class is that I have all of you for this class in the same lab. So we can cover this and addition and subtraction at the beginning of lab. And then we can leave these examples to do Monday. And so then, because we have not finished chapter 2, the homework's not going to be due on this Friday. It'll be due next Friday. So, yeah. It is, no, it's in 221. The chapter 2 homework is due next Friday. The unit analysis worksheet, because I'm going to talk about some of this stuff in lab, actually a lot of this stuff in lab. I will probably move the unit analysis worksheet back to at least next Wednesday.
So our homework is just chapter 1?
So homework this week is just chapter 1.